Okay, students, so I'm going to show you the washer method. I had the answer key on that, but I needed to record the videos. I thought the videos were showing up, but apparently they weren't. So I'm going to go ahead and go through the washer method. So the first thing I'm going to do is just show you kind of how this works. So let's suppose that you have two curves. You have f of x, and then you have g of x. Now the key thing on this is we're continuous. So we're looking at two functions that are continuous. God, I can't spell sometimes. Okay, so we're continuous on a to b. All right, like that. And we have two functions, f of x. On this interval a to b, f of x always has greater function values than g of x, and they're above the x-axis. So there's a couple things we're going to check on this. So what we end up getting, if you can imagine rotating this around the x-axis, the cross sections look like washers. All right, so one of the things I'm going to kind of show you on this that I like to do when I'm doing these problems, I like to just draw a graph, and then I like to draw my washers. So I'm going to put, just something kind of in here. That would represent the circle, the upper circle. Then I could do the lower circle here. Then I'll kind of talk about what this is doing. It kind of looks like a little donut there. So what happens is you kind of get this washer area here. This is what the cross section looks like, is it looks like a little washer like that. And if you're going to find an area of a washer, that's the whole key, is what are the dimensions of these cross sections. So first of all, you would kind of have, this would be the x-axis going, straight through the center of that washer. And we have two things we know. We know the area of a circle is pi r squared. However, in this diagram, there's two radius. There's the bigger radius, which I'm going to represent by a capital R. Okay, so that's the bigger radius. And then we have a smaller radius, which is from there to there, that I'll use as little r. So that little piece right there is the smaller radius like that. Okay, so here's what happens on this then, basically. It just goes like this. Okay, it's going to go like this. The area of a washer is found this way. This is basically what you do. Okay, it's just the area of the big circle, the bigger circle, minus the area of the smaller circle, like this. Okay, so what does that give them? Remember, pi r squared is the area of a circle, so you'd have pi capital R squared minus pi little r squared. So this would be the cross-sectional area of a washer, and then you can factor out that pi, and you get pi times capital R squared minus r squared like that. Okay, so that's how that goes. That's what's going on that washer then. So if you understand that, that'll help you to build these integrals, and the integrals are pretty easy to build. So the other thing is the thickness of this. That's where you get into the differential. That thickness is dx, because the washers are going this way. If the washers were going this way, then that thickness would be dy, like that, okay? So we'll look at the differences between rotating around the x and y axis. Okay, so that's kind of shows you that. This basically is going to show you this diagram down here. What this is saying is, this is the big radius, that's the small radius. So if you look at this washer right here, the big radius is given by f of x. The small radius is given by g of x, that's the lower curve. So what you end up getting then is you really ultimately get this formula like this. You get pi, and then you have the upper curve squared minus the lower curve squared like that. Okay, so that's upper minus lower. All right, that's it. So that's how that one gets put together. That's the mathematics behind that. So I'm going to go ahead and move on to the next page, and we'll look at the basic washer method integral that we'll be building on this then. Okay, I found some pictures of washers, of actual washers. All right, so let's see. With this one, it goes like this. So you have two curves. Again, f of x and g of x. F of x is the upper curve. G of x is the lower curve. This is what causes this to have a cross section of that's a washer, and they're both above the x-axis. That's what the meaning of that is then. Okay, the functions have to be continuous on that closed interval from a to b. So you're looking at a closed interval. So then it goes like this, all right? So basically your volume of your revolution, your solid of revolution, you're going to integrate from a to b, and then you have pi, and again, just think of this as capital R minus the little radius, like that. And then dx is just the cross section, like that. Okay, so that's it. So what we're going to do is we're going to put together several of these examples. Now this is a graph. If the graph's not given, then you probably want to look at your graph real clearly on your calculator. So I'm going to take you through all the major steps of finding the volume on this. The first thing that you'd want to do is you would really want to ask about the continuity. All right, so y equals 2 root x, okay, that is continuous where? All right, you can only do a square root of a positive number, so that would be continuous from 0 to infinity. So it looks like we're good there. All right, and then the other one, y equals x, well, that's a linear function. That's continuous everywhere. So we have the continuity. If we don't have that, we have some breaks and stuff, then we're going to run into some problems with that, finding that volume. So the second thing that you would want to do is find the intersection points. So with this problem, you'll need to set those functions equal to each other to find the intersection. Okay, so basically what I just do is this. I just plug in, I can just replace, and it doesn't matter which way I do this. I'm just going to plug that in there. So I get the equation, 2 root x equals x. We need to solve that equation. So the way we solve this equation is, you've got a radical, so you want to get rid of that radical. So when we do this, 2 to the second would be 4. If you square that radical, you just get x. The radical goes away, and then this side would be x squared like this. Okay? A couple of things on this. These little algebra things sometimes students mess up in this class. So I like to just sort of go over this stuff, but you just have 2 times 2 is 4. Radical x times radical x is radical x squared. And if you do the square root of anything squared, it's itself, so that's 4x. So then what I'm going to do is I'm going to do this. You can solve this equation. One side needs to be equal to 0. Doesn't matter which side. I'm just going to slide the 4x over here to get x squared minus 4x equals 0. And then we can solve this by factoring. So we have 0 equals x times x minus 4. So that gives x equals 0 and x minus 4 equals 0. So you basically get x equals 0 and 4. So what you can tell on the graph here is this point right here, you have x equals 0. And then this point right here, you're going to have x equals 4. So that's going to help us to set up our integral then. And then we're looking at this shaded region like this. Okay? So now we want to kind of see what our washers look like. And you don't have to do this every time you're doing the problem, but you're going to see me do this because I want students to understand how to build the formula rather than just looking at the washer formula all the time, as students sometimes tend to do. So what I always like to do is just draw the washers. That's my big circle. And then I'm going to draw my little circle. Doesn't have to be perfect, just needs to give you a kind of a rough idea of what this washer looks like. So we have something that kind of looks like that. And essentially, what you have is you have this region right there kind of makes up your washer like that. Okay? It's a pretty good washer. Okay. So what I'm going to do is I'm going to just use this little washer over at the side to represent everything then. Okay? So again, the center is your x-axis. So what do you have? You have a big radius and you have a small radius like that. Okay, so the third thing we're going to do is we're going to do the area of the washer, the cross-sectional area of that washer. So it basically goes like this, and you don't have to write every step like this. It's pi big R squared minus pi small r squared. R is represented by the upper function, capital R, and little r is represented by the lower function. So what you would get is pi, and then you can factor that out to get this. So what we end up with is pi times the upper curve, which is 2 radical x squared. Lower curve is x squared. So it's really pi r squared, capital R squared minus little r squared right there. Now we're ready to set up the integral. So essentially this is pi. You square this, that'll give 4x minus x to the second. So that's the function that gives the cross-sectional area, all right? And then dx is going to be what we have in our integral then, and we're going to be integrating this way, okay, from 0 to 4. Step 4, set up the integral, and then see if we can do that. So what I'm going to do is I'm going to set up the integral, and then I'll let you pause the video and let you go ahead and do this one yourself and see how you fare. So the volume is going to be the integral from 0 to 4 of this cross section. That's the washer. That's how you represent really the area of that washer. And then dx. Okay? So see, what you're really doing is all of this together gives you the volume. That whole thing right there is the volume. And what you have is the cross-sectional area, which is this, and then you have the depth, which is this. Okay? So if you get that down, then this stuff should make perfectly good sense to you. Okay, so you're on your own to go ahead and work that out. I'm going to go ahead and have you pause the video. I'm going to work it out and let you see how you did. The other thing I would recommend you do before you resume the video is graph this on your calculator. You know, just go Y1 on your calculator, set up a pretty good viewing window, and do your numerical integration to see if your answer turned out to be correct. Okay, so go ahead and pause, and we'll see how you do. Okay, so 32 pi over 3 is what you should have got. So you just need to check over the work on that. Make sure that you got everything correct. If you made any mistakes, you want to go ahead and get that corrected. Okay, I was going to show you how I do this on the calculator next. So I put it in like this. So I went ahead and just put in, this is y. So I went ahead and set that up on my calculator like that. I set my window up like this, and I did -1 to 5. It's always a good idea to go a little to the left and a little to the right of your limits of integration. Particularly if you have an irrational number in your limit of integration, that can cause a little problem. So again, I got the graph. Looks like that. I go second trace, option 7, lower limit is 0, upper limit's 4. That's so satisfying to me. So we get this. That's the value of that integral, so that would be the volume. And just take the answer we got, 32 pi over 3, and then see if it matches. So 32 pi over 3 is going to give same thing. All right, that's how you do it then. All right, so that would be how everything gets verified with technology using your graphing calculator. Okay. All right. So look over that if you have any problem with that. Just get that corrected. You see any arithmetic mistakes? Pretty easy to make some arithmetic mistakes on these sometimes. All right, so this is a good place to pause if you need to look over anything. Otherwise, let's move on to the next page. Okay, so we're going to look at this situation. Okay, so let's go ahead and let's run through this then. So let's see. These two functions are continuous. So we're good there. We're going to go ahead and start by setting up the area of the washer. Okay, so remember it kind of goes like this. Let's go ahead and let's draw our diagram. You can bypass this if you feel pretty confident with this, but I like to, oh, that's not what I meant to do. Let me kind of use a different color here. So let's draw the washer in here. I'm going to draw the upper circle, kind of like that, and then I'll draw the lower circle. Doesn't have to be perfect, but you just got to get the kind of the idea here. Then the lower circle here, and you'll have something that kind of looks like a donut. Okay, so that's the washer. So again, if you kind of look at this washer that I have over at the side here. Oh, come on, my dang mouse isn't working. Crap. Come on. Okay, so if you look at this, so it kind of goes like this. Again, the idea is this is your x-axis. So you have the big radius, we'll use capital R. And then we have the smaller radius that we'll use little r on. So the washer goes, area big circle is pi capital R squared, little circle is pi little r squared, like that. So, and you can set this up. So the upper one, r squared, is the function that's on top, which would be this. So you would just have pi times e to the x over 2 squared. And then the function on the bottom. Okay, so the lower radius would be this curve. So that's going to be e to the negative x over 2 and then squared like that. Okay, so let's kind of clean this up a little bit. Might want to go to the side and review a little bit of algebra things on here a little bit. So here's the first thing I want to just kind of do over at the side here, a little algebra. So we have e to the x over 2 squared. There's two ways to look at this. One way is you're multiplying something by itself. So you add the exponent. So that would be e to the 2x over 2. So that's e to the x. So that's one way to look at it. Of course, the other way is multiply the exponents. A little algebra background. If you add x to the third to the fourth, you have x to the 12th, right? Okay, so this gives pi times e to the x. And by the same argument, this becomes pi e to the negative x. Like that. So that would be your cross-sectional area right there. And then what we can do is just pull that out. So we have pi e to the x minus e to the negative x, like that. So that would be our cross-section. And, you know, for graphing on the calculator and everything, that's what you would put in your calculator and numerically integrate them. Okay, so step 3, we'll set up our integral. So the volume is going to be the integral from ln2 to ln3. We're integrating x direction left to right, so it's ln2, ln3. And again, we can pull the pi out. And we have e to the x minus e to the negative x times dx. So again, I want to stress to everybody here, what I'm highlighting in green, that's the area of the washer. And then this is the cross section. So dx like that. So all of that together gives you the volume of that washer. And then you're integrating, summing up all of those washers with an infinitesimally small thickness. That's the idea. Okay, so let's integrate this and see what we get. There's a few little algebra things that I'll remind you of as we go. So we can go ahead and write this as pi times the integral ln2 ln3 e to the x minus e to the negative x times dx. Okay, so a couple of things I want to do over here now for a little algebra review here, because students need this from time to time. A little calculus review too. The integral of e to the x dx we know is e to the x plus c. Now the integral of e to the negative x dx is negative e to the negative x plus c. You don't have to do u substitution on this. Another thing that I'd recommend everybody know, if you don't know this already, is if k is a constant, the integral of e to the kx dx is 1 over k e to the kx plus c. And if you know that formula, it keeps you from having to do u substitution. And you do this enough in this class that you should know those three integrals right there. Okay, so let's go ahead and work it out. So it looks like what we're going to have is pi, our antiderivative is e to the x, minus, and then see the answer to this antiderivative is this. Okay, so that would be negative e to the negative x, and then that gets evaluated from ln2 to ln3. Okay, like that. Okay, so let's go ahead and work this out then. So we're going to go ahead and evaluate. So what we'll have is pi, and let's see, I'll go ahead and write one more step. This is really e to the x plus e to the negative x. Then we evaluate from ln2 to ln3 like this. So this will be pi. Plug in the upper limit. We're going to have e to the ln3. Let's do one more thing on this. I kind of prefer to do it this way. I mean, you can skip some of these steps, but I'm trying to show it as clearly as I can. So this is e to the x plus 1 over e to the x. Evaluate from ln2 to ln3. And then we'll wrap this up here. Okay, so I get pi times e to the ln3 plus 1 over e to the ln3 minus, now the lower limit would be e to the ln2 plus 1 over e to the ln2 like that. All right, so a little algebra background. Okay, so algebra, let's see, there's a well-known property that says if you have p to the log base p of x, you get x. You probably would have seen that in pre-calc or college algebra. So if you had like e to the ln of x, that's x. So if you have e to the ln3, that's 3. Okay, so we work this out like this then. We have pi times e to the ln3 is 3. This would be 1 over 3 minus, and then this would be 2 plus 1 over 2. If you don't know that, your calculator will bail you out on that then. So what we'd have then is we would have pi times 3 plus a third minus 2 minus a half, like that. Okay, that gives 3 minus 2 is 1. So I'm going to kind of do this like this. I have 1 plus a third minus a half, which you can do your calculator if you want to on that. If you get common denominators, you would have 6 over 6 not 4 over 6, come on. 2 over 6 and 3 over 6, like that. So that would end up giving pi times 5, 6. So the answer should be 5 pi over 6. Okay, so I've got that. That would be the answer to example 10 then. Now what I'm going to do is I'm going to show you how to quickly check this on the calculator. And I think I've already got this one put in, so you can just watch, or you can do this with me if you want to. Okay, so I put in this right here. I put in pi e to the x minus e to the negative x. For the window, I did like this, I think. Pretty good viewing window. Graphed it. Okay. Second trace, option 7. Lower limit is ln2. Upper limit is ln3. Just put it in like that. That gives 2.6. Okay. So we get that, about 2.6. Can maybe move this thing over at the side here. And then what you would have on this is you could just check your answer. Okay, so notice 5 pi over 6 is 2.6. So that does match very nicely with that. Okay, so that would be it on that particular problem then. All right, so this is a good place to pause if you need to look over any of the things I did on here. And then that graph will verify that we got the right answer. Okay, otherwise I'm going to move on to this example. Now we're going to go around the y-axis, so it's a little bit different on here then. Okay, so now we're going to revolve around, let's see, I think I'm too far ahead. There we are, example 11. So we're going to revolve around the y-axis. So the washers end up, are flat washers now. So I'll kind of go back up here and get this guy right here and kind of show you how these go. So I'm going to paste this over here. And what happens in this situation, you want to first of all see why we have the washer that we do. So first of all, with this we have two continuous functions. These are both lines, so they're continuous. We don't have to worry about that. So let's draw the washer on our diagram then. So it doesn't matter where. I'm just going to put one circle kind of like that, I guess. And then I'll put a circle inside of that. Kind of going from here to here. Just so you can kind of visualize what's going on there. Okay, it's a little hard to get these things perfect, but you'll get the idea. Okay, so what's going to happen on this one then, if you consider this now, you kind of have this little washer area going around like that then. All right, so let's put this together in this diagram here. So what happens here is this would be your y-axis going through the center kind of like that. And then you kind of have the same situation. You have a big radius that I'll call R, and then we have a smaller radius that I'll call little r like that. All right. So what we're going to do is we're going to go ahead and set up our integral on this and see if we can get this put together okay then. Okay, so let's go ahead and let's do the area, the cross-sectional area of the washer. Okay, so same situation. We're going to have pi big R squared minus pi little r squared. All right, now what's different about this now is we're going to have a dy thickness. So that means the integral has to use the variable y in it. We're going to have a dy integral. So what that means that we're going to have to do is these radius are going to be x values. Okay? So first of all, what you want to do is take this equation, y equals 2x, which is this line right here, And you got to solve that for x. So we're going to divide by 2. So we'll end up getting, from here we get y over 2 is equal to x. So what happens, and you can draw these things in the diagram if you want to right there, this part right here, that will be the little radius. That actually is y over 2. And that's going to change as these washers move from the x-axis to 6. Okay? Then the other one we just have x equals y. All right, so that what that means is this radius right here is going to be represented by the x value, which is given as y. So capital R is going to be y like that. All right? Okay, so basically it's going, you're using these equations, but what they are doing is they're given x values. Okay, this is, you know, that's really the big R. That's really the small r like that. So if we continue with our area of our washer, then what we're going to have is we're going to have pi big R is going to be represented by this. So that's y squared minus, and then pi little r squared is going to be represented by y over 2 squared like that. So that's what that gives. So that cross-sectional area is going to be pi y squared minus pi times y squared over 4. So if you factor the pi out, that would be pi times y squared minus y squared over 4, like that. And of course you could go ahead and just get a common denominator on that, and what you would end up getting here would be pi times, and you can get a common denominator, this is really 4y squared over 4 minus y squared over 4. So that's actually equal to pi times 3y squared over 4. So that's what our cross-sectional area is 3 pi over 4 times y squared. Okay, so now we're ready to set up the integral. So that's it. So the difference in this is, since you're doing a dy integral, the integration is going in the y direction. The thickness of the washer's dy, these things have to be expressed in terms of y. So that's why we use x equals y and x equals y over 2 like that. Okay, now when we set up the integral, then it's going to go like this. Okay, so the integral, the volume is going to go like this. We're going to integrate from 0 to 6. Our cross-sectional area is 3 pi over 4. Y to the second times dy. So that again is your washer area, and then this is your cross section. So together these actually give the volume of that infinitesimally thin washer. Okay, so go ahead and pause the video and work that out. It's a real easy integral, so you like it when it works out that way, and then come back and we'll check the answer. Okay, so 54 over pi is what you should have got on that one. Now, even though this is a dy integral, you can still do this on the calculator. So look over the work on that, should get 54 pi. I'm not going to probably check this on the calculator. But again, all you'd really have to do is do this on your calculator. You could just go y1. Instead of putting a y in, you could do you could go like 3 pi over 4. You could probably put it in kind of like this. Got to be kind of careful about how you put the fraction in. So one way to do this would be like 3 pi over 4, and then y to the second, but you'd have to put an x to the second in. It should give you the same calculation. I'll go ahead and just do that real quick here. So I'm going to put in parentheses 3 pi over 4. So that's the constant, and then times x to the second. We're really doing the integral from 0 to 6. So I'm going to go maybe 0 to 7, just a little bit bigger. Do a graph, and then we'll see what we get here. So I go second, calc, option 7. we're going to integrate from the lower limit of 0, upper limit of 6, and that gives this. So 169, let's see if this isn't right. So we go 54 pi was our answer. And how about that? So it's the same. Okay, so that's how you would get that one done. See, the basic idea is the dx integral on your calculator does the same arithmetic. That's why that works out okay. All right, good place to pause if you need to look over that. Otherwise, we're going to move to next page. Okay, so let's wrap up this last example when you revolve around like a horizontal line. So this time, instead of going around the x-axis, we're actually rotating around this line. So this is kind of creating a shape that's going about that line like that. First thing I'm going to do on this is I went ahead and just graphed this on the calculator. This is y equals square root of x, and then the lower curve is y equals 1. So we want to find that. We're going to go from x equals 0 to x equals y equals 1. So this point right here, the intersection point, you can do in your head. So it goes like this, so you don't really have to do this, but you just have square root of x equals 1, set those two curves equal to each other, square both sides, you get x equals 1. Okay, so x equals 1 is where that's going to go, and we're going to go from, we're going to be bounded by the graph x equals 0, which is just this line here. Y equals 1 is what we get revolved around like that then. Okay, and let's see. So we're bounded by this. We're bounded by y equals 1. The red line I've got there is what it gets revolved around. So we're actually looking at this region right here. Okay, so I'm going to just kind of shade in what this region is that we're considering right here. And we're considering this little area right here. Now what's going to happen is that gets rotated around that line. So you end up kind of having, think about how that looks as it goes through kind of like this. So it's going to look kind of like this. As this thing gets rotated around that line, kind of looks something like that. So actually we're going to have that. We're not going to be looking at this region out here. I mean, you could, but the problem doesn't really say that. The problem is implying that we're looking at the area bounded by y equals 1 and y equals square root of x, so we're going from here to here. All right, so first of all, this is not a washer. This is a disk. So you always got to look at that. When you get your graph, you got to consider what it is. So what I'm going to do is I'm going to draw the disk around this thing. So this is just simply a disk method on this. So I'm going to just draw a, whoops, that's not what I wanted to do. I want to draw a disk around this. Okay, so your disk could kind of look something kind of like that. Okay, now I'm going to draw, just kind of superimpose this and just draw a picture of this disk kind of down here. So it's not a washer. So what you have here is you've got this line, y equals 1, and then you've got this curve that kind of goes like this. You've got the radius would be right here. So that's your radius. Remember, the area of the disk is pi r squared. So what that is this curve here is y equals square root of x. So it's the distance between those two things. Okay? So basically the radius on this would be 1 minus the square root of x. Okay, think about it. See, that radius changes everywhere. The radius right here is 1 minus the value of the square root of x. 1 minus the value of the square root of x until you get here. All right, so it's going to go like that. Now we're going to have a dy integral, a dx integral this way. Okay, so the disks are going this way, so it's a dx integral. The thickness is dx. Okay, so the area of the disk is this. It's just basically pi r squared. However, the radius is given by the function 1 minus square root of x squared, like that. So that's your cross-sectional area that we get there. So now we're ready to set up the integral. Okay? There's more than one way to do this problem. This is just kind of the way I like to do it. Just look at the line, figure out if you have a disk or washer, if you have a disk in this. So the volume is going to be the integral. And again, we're going from 0 to 1. The problem said you were bounded by the y-axis, so we're going 0 to 1 of pi times 1 minus square root of x squared times dx. Okay, so again, as we've been seeing, that's your cross-sectional area of a disk this time. So that's the disk area. Okay, and then this part right here is the cross-section. Okay, that's the infinitesimal width of that disk. All right, so what I want you to do is I'm going to have you pause the video and work the whole thing out and see if you get the answer as soon as you do the video. Go ahead and you can look over what I'm doing here. See if you get the same answer. Okay, so the answer you should have got is pi over 6. So what we're going to do on this, I am going to kind of talk through what I did on this. There's some algebra on here I'll go through a little bit. So basically I FOILed this out. So I just did 1 minus square root of x, 1 minus square root of x. You'd have 1 minus x minus square root of x plus x square root of x squared. So you get 1 minus 2 radical x plus x if you FOIL that correctly. Got to be careful about issues like that. So it gives pi times this. I pull the pi out. I rewrite this as 1 minus 2x to the 1/2 plus x. Then I integrate. So the integral of 1 is x. The integral by power rule of 2x to the 1/2 is 2x to the 3/2 divided by 3/2. So multiply by 2/3. Okay. And then the integral of x is x to the 2nd over 2. So this is your antiderivative right here, x minus 4/3. And you can write that back as square root of x to the 3rd plus x squared over 2 from 0 to 1. And all the work here is just the arithmetic of evaluating. You can look over that. So I got pi over 2. All right, so that'll wrap that up. And let me know if you have any questions on the washer method.